Hello and welcome to the Sustainable Materials Management webinar series, a joint effort between the National Recycling Coalition and the Pennsylvania Recycling Market Center. My name is Wayne Bowen. I'm the program manager for the Recycling Market Center and will serve as your moderator today. Today's webinar topic is Advancing Circular Economies in Electronics Recovery. Our presenter today is Carole Mars, who I will introduce in a moment. Following her presentation, we will conduct a question and answer session. If you have a question or comment, please use the Q&A feature box located on your control panel on your screen. You may also use the chat feature to request assistance if you're experiencing technical difficulties during the webinar. Please note that an edited version of this webinar will be made available for viewing via YouTube links on the National Recycling Coalition and Pennsylvania Recycling Market websites. And also please note that Pennsylvania Recycling Market Center, its affiliates, funders, and the National Recycling Coalition assume no liability resulting from the use of any information provided during this webinar. The webinar is only provided as an informational tool and no discrimination is intended and no endorsement by these organizations is implied. And now I'd like to introduce our presenter. Dr. Carole Mars is the Director of Technical Development and Innovation at the Sustainability Consortium at Arizona State University. She is responsible for the development of thesis, KPIs, and related information on sustainability issues and improvement opportunities in manufactured goods supply chains. Her research is focused on the consumer electronics and battery industries with an emphasis on product fate, end-of-life management, and the circular economy. She also serves as a technical advisor to the Responsible Battery Coalition. Prior to joining the consortium, Dr. Mars worked as a process engineer in the semiconductor equipment manufacturing industry. Dr. Mars earned her PhD at Penn State University in surface analytical chemistry and her BS in chemistry at the University of Arizona. And now I'm going to turn the program over to Carole.
Hello, thank you. Thank you, Wayne, for the introduction. Can you hear me all right?
You sound good.
Perfect. All right, then we'll go ahead and get started. So I am Carole Mars, and I work for a group called the Sustainability Consortium. And my research interests and one of the work streams that we've had up at the consortium lately has been about circular economy. And through my work with the Responsible Battery Coalition, I've had the opportunity to start really looking at the question of batteries. I think it's something that's really on everybody's mind right now, whether it's the vehicle batteries, whether it's the fires in materials recovery facilities. Batteries tend to be very top of mind. And so what I'd like to do with this presentation is to kind of take a step back and look at some of the challenges of battery management and where the real pain points are right now. I noticed that there's a fairly broad expertise and experience variety across the attendees. So hopefully everyone will still be able to pick up something interesting and useful out of this. So just as to start, I do work for a group called the Sustainability Consortium. We are housed jointly between the University of Arizona, I could get in a lot of trouble for that, between Arizona State University and the University of Arkansas. And we're focused on sustainability in consumer supply chains, consumer goods supply chains. So how best do you improve the sustainability of consumer products that are reaching the shelves? And so we've spent a lot of time looking at supply chains and thinking about, how do you best assess materials and materials moving through systems and the implications of those materials moving through systems, which is sort of what's brought the consortium to our work in circularity. Just as a starting note, I think everyone's familiar with the fact that there are systems, and these three examples are just three of many, and many more that are launching on a frequent basis, that really the materials that are moving through the electronics chain, the OEMs have really spent a lot of time thinking about what they can do better with the materials and how can they make these products circular so that they are not constantly drawing on new materials. One of the big challenges with that, of course, is that a lot, or probably everything now that would be considered a consumer electronic also requires a battery. And so we tend to think of batteries in a couple of different silos, but I'm going to be talking about them kind of all together. And so the first batteries that, at least it's kind of a history of how I've gotten involved in the industry, the lead acid battery systems. If you were in a car today, you've probably interacted with the lead acid battery, but they're also found in consumer electronics, UPS backup systems, smaller applications like that, the small sealed lead acid batteries. And so lead is interesting if you're talking about what you can do with batteries, because really it is really a fantastic example of a designed closed loop system for materials management. And not that the industry is without its issues, but as far as getting the batteries back and getting them back into new batteries, it really is an exemplar across all of the consumer goods space, really. As far as when you're talking about electronics, this would be your smaller lithium ion batteries, the lithium cobalt oxide chemistries that are found in your cell phones and your tablets, predominantly with these, which is in contrast to the lithium ion chemistries that you find in automotive applications. So the larger platforms are different chemistries, and they are quite complex chemistries, as you can see by the letter soup that describes the chemistries. Right now, as far as recycling batteries, some work unpublished work that we were looking at last summer, about 20% of what an electronics recycler brings in is a battery. They constitute by weight roughly 20% of what electronics recyclers see, and the most of those are lead acid or alkaline, with a significant portion of lithium following behind them. Now, we don't really know what the amount of batteries that will be available from automotive yet, because these have not yet started aging out in large numbers, which provides a set of issues unto itself. So, stepping to look at what's right and what's wrong about the lead acid batteries. To start at the beginning, lead acid batteries are actually very simple in their design and construction. And this has been a huge advantage, that pretty much regardless of the manufacturer, all lead acid batteries are lead oxide, sulfuric acid, and a case of usually polypropylene or some other rigid plastic. Very straightforward and easy to get your arms around. They are inexpensive. They have a very wide range of temperatures that they can operate effectively at, and are still used for SLI applications, so starting, lighting, and ignition in automotives. And if you look at the supply chain for it, it's really been very, very successful. 99% recovery rate for lead acid batteries. But if you look at the supply chain as a whole and the impacts of it, you certainly have serious concerns about lead exposure. And that is actually really the primary issue with this supply chain, is lead exposure from secondary smelters where batteries are being recycled, and then legacy issues where there was a smelter or there was some sort of battery material recovery that had since closed and the company went away, but the land that it was on is still contaminated with lead, but there's not necessarily any note or recognition of that. So I expect to be seeing more about that in the near future. So the story with lead really, though, is that it is its closed loop success. The entire battery is recoverable. At least in North America, we're getting back, the industry recovers 99% of what's out there. Of each battery, 97% is recyclable. And of a new battery, 60 to 80% is recycled content, although that tends to vary for automotive applications in particular, where an automotive OEM may have specific requirements for virgin material or new material going into batteries and don't accept recycled content. And then one of the things that I think I find most interesting about what's been done by the lead industry is that 75% of the lead used in batteries is recycled. And over the last few years, there is now more secondary lead in batteries and recovered annually than primary mining sources. So recycled lead now out, there's more of that than actual virgin lead that's been mined. So it's sort of a interesting success that you don't see in any other industry, where the system has been optimized to the point that that more recycled content than virgin material is used on an annual basis. And I would expect that you're going to be hearing more about this over the next year. The lead battery industry will be spending a lot of time talking about their circular economy stories because it really is impressive what they're able to do. We'll talk a little bit later on about what we might be able to learn from the lead acid battery experience. And as mentioned, it's not without its issues. This is another space that you can be watching in this spring. There should be some reports, I believe, in April from UNICEF and Pure Earth, looking explicitly at the issue of contamination and childhood health, and how, and pretty convincingly tracking that lead battery recovery systems are the greatest source of lead exposure to children. And so we'll be able to see how that story plays out over time. But there are also organizations and the manufacturers themselves that are very tuned into this, and I'm sure we'll be hearing from them as well. So to the, I guess you could say, chemistry of the moment, are the lithium ion batteries. Now, in comparison to their lead acid counterparts, lithium ion batteries are far more complex. This is a schematic of one of the manganese-based ones that would be more common in automotive applications than necessarily your cell phone, but the structure is pretty much the same. You're looking at multiple layers multiple layers of materials put together in a sandwich structure. Whether they then put those structures in a pouch or roll them into a cell, depends on application. But they are quite complex, and there is not only a lot of variation in the cathode lithium materials, but also in the other materials that are necessary to make those batteries work. And a lot of the challenge with them is the looking at the electrolyte. So there is a liquid electrolyte, and when you see cars going up in flames, it is the electrolyte that's burning, not necessarily the lithium itself. And the end point of a very large fire, where what material is burning isn't doesn't change the fact that the car is burned, but it also opens up opportunities to make batteries safer. There's quite a bit of research going on at universities and other institutes on moving into a lithium polymer battery or solid state batteries that decrease or eliminate that electrolyte. So hopefully, in that sense, the battery itself will be safer. As far as recycling batteries, we look in at what the options are today. And so there's three primary flows. The first one is smelting. This is a pyrometallurgical system that would be take it, put it in the smelter, recover your heavy metals, which is certainly probably where the majority of batteries are ending up today. The second process that's at scale is hydrometallurgical, or hydro, which is where you're using a liquid aqueous-based solution to pull the metals out. And so you can get to your lithium and you can get to your aluminum and some of the lighter metals that you're not going to be able to separate out of at a smelter. The challenge there being, of course, that is a chemistry specific process. So what you might use for a car battery is probably not going to work for a cell phone battery. And then the final, which is these two technologies are really fairly well established because they come from the mining industry. So they have been adapted to use with batteries, but not necessarily designed with batteries in mind. Now, there's an emerging process called direct recycling, which actually is designed specifically with lithium-ion battery chemistries in mind. The idea is to preserve the materials rather than just like breaking everything down to their element. The idea with direct recycling is that you're going to be able to, pull some of those components out, cathode in particular, so that lithium-ion complex, without breaking it down into its constituent parts. So instead of recovering lithium and manganese and cobalt, you would recover lithium, manganese, cobalt oxide. So that material would then be able to be put directly back into batteries, saving multiple steps in refining and reconstructing the lithium ion, the lithium materials. This, however, has not been demonstrated at scale yet, although there are some very, very active research efforts to make this happen, as it is seen as a route to making lithium-ion battery recycling cost-effective, which currently it's not. So, stepping back also and looking at what else is happening with lithium as with lead, and as you would expect, we really don't know all that much more about the lithium. Certainly sourcing, I think we are only on the beginning of hearing about issues with lithium sourcing, in part because it just has never been done at the scale that's being required. And not just there's certainly a scarcity, but also just the overall environmental impact of these minings really hasn't been seen, hasn't been understood. So I expect that is going to become a serious issue in the next few years. One other note that there's sort of a tangent here is that within the use phase, when considering sort of circular and how to keep these materials in play, part of the focus is to extend the use phase. How do you keep a battery being used as a battery as long as possible? So that definitely the reuse and refurbishment with the lithium-ion batteries, but we also, through the Responsible Battery Coalition, have worked with the Center for Sustainable Systems at the University of Michigan. And this spring they will be publishing some work that they've done on charging systems. So how do you treat your battery during its first use to make it last longer? and what are the considerations there. And I do believe that study covers both the smaller batteries, your consumer electronics, as well as large-scale charging. So should be interesting, something of a different bent than a lot of what than a lot of the different conversations. So I would recommend looking out for that. Then looking at what you have as far as lithium-ion battery recycling goes, there really are a lot of questions about how all of these pieces are going to go together, and it will certainly not be in the nice, tidy, neat line that has been diagrammed here. And then just briefly on material sourcing. So this is a study that came out a few years back now about materials, and that it's the expectation with something like lithium is that it's not going to be physically constrained. It's not like there isn't enough of it. It's just as with cobalt, it tends to be in areas that will have political constraints or political scarcity, where you might be able to get the material, but at what cost? So this will be an ongoing story moving forward. Although I think the story that certainly has captured headlines is the question of stranded energy. Even if the battery itself is safe, is quote unquote safe because it's a solid state battery, or it's polymer and the electrolyte's been eliminated, you're still talking about energy storage systems. So, it's the idea of stranded energy being that there is still power in the battery left, and it has to be managed in such a way or you will get major issues. There is also, in addition to the stock pictures of trucks burning, there was a train outside of Houston a couple years ago that also went up in flames that was transporting lithium-ion batteries. The sense that I get is that it's not a question of if there will be a major issue moving batteries around, it's just when and where. And along with that is expected a run of legislation and regulations to go along with that. And so I know that there's certainly in the automotive industry a lot of interest in not getting to that point, and what kinds of steps can be taken in advance to not get to the point where the solution becomes regulatory rather than industry based. So that's sort of the batteries themselves and the systems that they exist in. The goal is certainly to get the lithium ion to the same point that the lead is already at. Greater than 90% recovery with materials that are going back into creating new batteries. Now that's a worthy goal, but it's not without its serious challenges. So, thinking about how do you where are the challenges, where are the barriers that are going to need to be addressed to see this vision of circularity. On the consumer electronics side, what used to be separable batteries are now becoming embedded batteries, which not only complicates it complicates the recycling. If you can't get to the battery, you certainly can't get it to recover, whether it's a hazardous waste or not. You can't get to it to recover it. You can't do anything with the product that it's embedded in, if you even know that the battery is in there in the first place. And certainly batteries in the municipal waste streams. I think that's probably a very sensitive topic for this group in particular. that I wish I could tell you I had a silver bullet to solve all those problems and keep batteries out of MRFs. Unfortunately, I don't. But that's, I think, going to be on the consumer battery side. The big question is, how do you collect and manage all of those little batteries that consumers may not even know are in their products? So I see that as being one of the defining issues within the next year. It's interesting seeing how much regulatory activity was happening, or it's not regulatory yet, it was still legislative. Legislative activity was happening at the state level around batteries. So it'll be interesting to see if any of that trickles up to a federal level, like we've seen with single-use plastics and recycling. And then the third point here is multiple chemistries and similar formats. Certainly the question of how do you sort alkaline from lithium, from zinc, from whatever other chemistries are floating around there at the small size. You know, a AA battery is sized the same regardless of what's inside the steel canister. You know, this is one of the advantages of pyro recycling, is that they can all go in and you're recovering the steel of the casing anyway, regardless of what the cathode material is. But there's also the question of mixing larger batteries, because what the lead recyclers are finding now is that lithium batteries that have been sized and shaped to go into cars to replace lead batteries are now finding their way into the lead battery recycling systems. And when they hit, it's essentially a smelting process. And so when the lithium battery hits that, you're having explosions within lead recycling facilities, which, you're already looking at a material that has known consequences to human health, and now you're adding an element that's causing them to explode. So, there's the idea of how do you sort out by battery chemistry is what I would be looking for as one of the major kind of a technology solution that could really make a difference here. And then there's just the economics of battery recovery. As amounts of cobalt are decreased in batteries, cobalt in particular, the overall value of the lithium ion batteries is decreasing. And it is becoming a cost, a strong or a greater cost than it has in the past to be able to recycle these materials, because there's no more market for the other side. One of the lithium batteries of particular concern in that space is the lithium iron phosphate that is being touted as the replacement to lead. And the problem is that there is no end market for those materials. Yes, you can recycle the iron. Yes, you can recycle the phosphate, but there's no markets for those materials to go into. So, there's the question there is that, okay, it's not lead, but what new issues are you introducing to the system that are going to challenge recovery later on? And then of course, the large format transportation utility scale batteries, couple of different challenges with those. First, with the automotive, it's very hard to design a system when you don't have batteries to test. The only large scale batteries, automotive batteries, that are coming back right now are either in a catastrophic situation, failed testing at the manufacturing facility, we returned for defects of some sort or another. So they're not really in high volumes yet. So there's a lot of guesswork going on right now of how do you manage these materials that there's maybe not a strong domestic infrastructure to recycle these, and how do you deal with that? There's also the additional challenge that the chemistry of the lithium batteries is evolving over time, and when you get into utility scale, it may not even be lithium down the road. So you will be needing to recycle lithium batteries many years after that chemistry has sunset. So maybe the the batteries, the battery industry can learn from the experience with cathode ray tubes in electronics that you still have to plan for obsolete technologies because they are going to be coming back at some point. So if you were to say, so what I take away from the lead acid battery systems that can be used, sort of the lessons learned that can be generalized regardless of the types of systems you work in, is that, the complexity in design matters, and also standardization of design. Although this is even starting to be challenged a bit. Up until the last few years, a lead acid battery was a lead acid battery, and it pretty much didn't matter who was manufacturing them. It was all still the same suite of materials, maybe just put together differently. But that's actually starting to change now with advanced lead acid batteries, where you're getting carbon and other additives to make the lead acid battery last longer. And so it'll be interesting to see over the next couple of years what, if any, impact moving away from the standardized design that's worked for the last 30, 40 years, how that's going to change. One aspect of the lead acid battery system is that actually regulations can contribute. Regulations certainly helped inspire the industry to decide what they were going to do with used batteries. And one of the probably the most effective things that came out of it is the idea of core charges, which for something like lead acid batteries or automotive batteries is a bit more tractable than trying to do a core charge for AAA batteries that consumers are buying at the local grocery store. But there is something to the idea of that giving consumers an incentive to get the batteries back to the right places so that they can be dealt with. And then something that I've had a couple of interesting conversations with people in the industry about is that there's an intentionality of design at this point. The system, the lead acid system, is vested in being able to get those batteries back and made into new batteries, used batteries back, getting the batteries back into the system. And so that actually plays an active part in design considerations. If you change something, are you going to disrupt? Is that design going to disrupt your ability to recycle that battery when it comes back? And so these really are the ideas that have come along from the lead batteries. It's not an apples to apples comparison by any imagination, but it certainly can be done, and it's a matter of figuring out the path forward. What I see for the lithium ion batteries, certainly dealing with the question of embedded batteries. For the smaller pieces, for the smaller electronics, that's going to be, that's kind of the question. The right to repair movement has certainly highlighted this challenge. And anyone who's ever met an electronics recycler will also have heard about this, because it's weighing quite heavily on the industry as a whole. In general, to move, I think that really the small format is the collection and aggregation. And as I said at the beginning, I wish I had the silver bullet on the collection side. But I think this is going to be the ongoing challenge. I don't know that there's been any legislation proposed that would be fully effective in moving to a more effective collection system. Unfortunately, I'm also don't have a lot of faith in the average consumer, being one. Even knowing what I'm supposed to do with my stuff, sometimes things don't end up in the best place, for whether it's a battery or whether it's a plastic container. And then I think with the large format, our we're going to be looking at how are you going to manage the volumes of batteries that could be aging out of automotives and scooters and buses and all of these other transport or mobility related applications. How are you going to manage those? Where are you going to manage them, since we do not have the scale of infrastructure, at least in the US, to be dealing with the batteries that we're going to be generating. This is actually already starting in the scooter industry, where there's a lot of questions about how to deal with the sheer volume of batteries that are coming out of those products. And then, of course, coming down to what is going to be the best recycling pathway, and is there a better material solution than just putting everything in a smelter? And so, just to kind of capture where the questions are for this. Sorry about that. Where the questions are in the recovery system. I mean, there's more questions than there are answers at this point. And I think a lot of the activity that's going to be going on, whether it's primarily in universities at this point, but trying to figure out how all of this is going to work is not going to be trivial. And then, just as a final note that'll be in this for you, is some of the ideas of what's coming next, at least on a larger scale. Some of the different methodologies that are not exclusively lithium based. This came from a group called the Joint Center for Energy Storage Research at Argonne National Lab. Then, so just as to close out some ideas. So there are people on this. As I've mentioned a few times through this Responsible Battery Coalition, which is really looking at more on the automotive side with an eye towards how can learnings there be useful to consumer electronics, because it doesn't make any sense to develop a system to recycle automotive batteries separate and distinct from a system to recycle smaller batteries. So I think that's also another trend you'll see, is that a lot of organizations that are involved in this are going to be starting to work in both sizes rather than treating them as isolated things. Recell is a new center at Argonne National Lab that is looking at battery recycling. They're leading up the efforts on direct recycling development, so something to watch. Call to Recycle, I'm sure you all are familiar with that, but really leading edge on dealing with the consumer side of the battery equation. The final group here is Global Battery Alliance. This is an effort of the World Economic Forum, and they're dealing more with the larger system issues. Lead battery recovery in developing countries, as well as one thing to not necessarily immediately relevant to municipal systems, but they're looking at developing battery passports so that every battery manufactured, it travels with its basically a history of where it came from and what the conditions of use have been. So we'll see how successful they are about it, but it's certainly an interesting idea. And so with that, we'll close there and see if there are any questions.
Okay, thank you, Carole. Great presentation. So now we're going to field some questions for Carole. If you have a question, please use the Q&A feature on your control panel. We do have some questions already. We actually got one from a person that called in, and so I'm going to try and unmute her, and hopefully she can ask her question. This is from Dawn. So I'm going to hold on a second here. Dawn, are you there? Guess not. Hello, Dawn. Hi, is this Dawn? Okay, it didn't work. Sorry about that. All right, so we have some other questions here. So this question is, lithium ion batteries have seen a drastic decline in scrap pricing through recycling over the past year. Do you know what is driving this? Is it the tariffs?
Oh, specifically tariffs? That I don't think so, but I am not an economics expert. I think that it's really going to be dependent. My understanding of recycling lithium ion batteries is it's dependent on cobalt content. And as companies for the human rights interests are decreasing the amounts of cobalt, and just in general, I think it's the overall depression of recycled markets. I would that those are the kinds of issues that are going to be playing rather than the tariffs specifically. Because if anything, I would more put it towards the national sword efforts that have upset recycling markets in general out of China. I would actually be more likely to lie changes in cost at the feet of that rather than the tariffs themselves.
Okay. Does direct lithium ion recycling also work with lithium primary cells? Why do the lithium primary cells cost so much more to recycle?
Again, economics not my strong point. The hydro processes for lithium are I don't know if there would be a process. Theoretically, there should be, but the chemistries that are used are specifically going after lithium oxides. So there's certainly a chemical difference between what you would need to capture lithium versus what you would need to capture lithium ion, lithium oxides, basically. They're different charge states. Why they would be more expensive? I think it's in large part because lithium metal batteries are primary batteries, so they're not designed to be recharged more. They are designed to be used once, and they are designed so that they have a much longer life than what your average lithium ion battery would have. And so I think that's going to be a big part of the delta in the cost. I would also not be surprised if on the manufacturing end there were higher costs in handling lithium metal, which is not known for its stability, that there would be additional costs incurred in manufacturing that might also contribute to cost or price.
Okay, here's some information on some future webinar. This has to do with transportation safety. The US EPA and the DOT are hosting a webinar called Safe Packaging and Transportation of Lithium Batteries for Recycling, What You Need to Know, and that is next month, February 23rd at 2 o'clock. And there's a link here to register. I'll try and get that to everybody, but that would be a good follow-up webinar for you folks. So next question is, are there any alkaline battery recycling programs that pay a scrap value for the metals rather than charging for the recycling process?
My guess would be no, because there's really not a lot of material value in an alkaline battery. There are, if you do recycle them, I know that one of the interesting facts I've come across is that the cathode actually can be recovered and sent to zinc sulfate producers, which is a fertilizer. And so used alkaline battery material is finding its way into agriculture because of the zinc manganese mix is good for crop rotation, but there's not enough value in that I would be surprised if anybody is actually paying for the materials rather than charging for transport costs.
Okay, here's a correction on that webinar. It's actually January 23rd, not February, so that's next week. Or actually, no, a couple days.
Yeah.
It's Thursday. So keep that in mind. How many states in the U.S. have implemented mandatory alkaline battery recycling, and how do they typically fund those programs?
I think that is an excellent question. I don't know. The only program that I am familiar where there's an alkaline requirement would be California, since they've banned everything, and I'm really not familiar with the funding of that and how California's managing that specifically on the battery side.
Okay. When you speak of embedded batteries, we're thinking of scooter/e-mobility, question mark, or the various lithium and other chemistry batteries housed throughout a vehicle, like tires, steering columns, and other areas of the vehicle.
Talking about embedded batteries, my thinking has certainly been more focused towards the integrated batteries in scooters, or even in consumer products, where you might have a battery that can't be replaced because it's better for product operation if it's integrated into the product itself. Although, interestingly enough, you don't hear a lot about the other embedded batteries within the automotive space right now. There's so overriding focus on the traction batteries that everyone else kind of gets left to the side. Although I think that's probably a very good question that I'm going to make a note on to follow up on.
Is there any interest in / action towards implementing a mechanism to temporarily prop up the lithium recycling industry until such a time as the wave of transportation batteries rolls in? We might be able to avoid a similar state that we dealt with the CRT televisions.
I have not heard anything along those lines. The closest to that I've heard as far as the lithium battery recycling, is that the DOE did have their the challenge that they posted last year and have since awarded grants for, that are looking at ways to make the system more efficient. But as far as supporting recyclers directly outside of programs like that, I've heard nothing along those lines.
Mm-hmm. And here's our last question, and this will be a good one to end on. What are do you have any safety tips that the public should know about transporting batteries for recycling?
Tape the anodes, or tape the ends. Cover the ends so things don't bump into each other.
Very simple.
And we literally have a recycling bin here that has a roll of masking tape attached to it. So it's like, please cover your terminals. That would be my advice.
Okay, good. Okay, so we're going to close it out. So again, this webinar, like all the webinars in this series, has been recorded, will be made available via YouTube links on both the National Recycling Coalition and Recycling Market Center websites. Thanks again for joining us, and we hope you'll join us for next month's webinar. And please visit the NRC and RMC websites for schedule updates. Have a great day, everybody.
Thank you.
Okay, so long.